Okay, so we're going to get started with our panel on Asteroseismology. Hello? Yeah. We're going to get started. So I'm going to first ask each of our panelists to spend 1 to 3 minutes introducing themselves. After that, we will do, similar to this morning, we'll break up into small discussion groups to discuss the problems that are listed on the screen. And then we'll bring it back and just have a discussion.
All right. Hi, everybody. My name is Vicky Antoci, and my background is in astroseismology of intermediate mass stars, what we call A and F-type stars. Don't go too far to the F-type stars because then they get all this convection, which I don't like that much. So what I'm trying to understand is actually the excitation mechanisms in these stars. Specifically, why do they pulsate? Is it just a Kappa mechanism? We know that the Kappa mechanism alone cannot explain all the stars. We know that the turbulent pressure in the convection zone, even if very narrow and very thin, still excites some modes. We also know that the stars have magnetic fields, which I'm particularly interested in a collaboration, in setting up collaborations at this particular program. Also, they have Raspy modes that we will probably hear more about, or we'll discuss more about, that are excited by magnetic fields. So it's, again, the excitation is not just the classical Kappa mechanism, but more than that. I've also worked with Gamma Dor stars, Delta Scuti stars, rapidly oscillating AP stars, which are very, very strong, have very strong magnetic fields, which we don't really model, but pretend we know what they're doing. I think that's mostly, so from the observational point of view mostly, but I've been also modeling excitations.
I'm Timothy van Reeth from the University of Leuven. My specialty or focus is more on gravity mode astroseismology. So these are oscillations that are dominantly restored by buoyancy. And my main interest here is to measure or to study the interaction between the pulsations and the stellar rotation. So if these gravity mode oscillations occur in a sufficiently fast rotating star, the Coriolis force will also contribute to the restoring force of these oscillations. And then you will also get these inertial modes and Raspy modes, and they will actually couple to the more normal gravity mode oscillations. And then the fun thing is that in addition to using the gravity inertial modes to measure the rotation, the oscillations themselves also carry angular momentum. So they also will actually influence the rotation profiles themselves, and that's something that we don't really understand yet at all. So yeah, that's very much my main interest.
Okay. And on that side of the panel, we are more about more evolved stars. So we did the main sequence, and we're on the subgiant branch and the red giant branch. So I'm Lisa Bunier. I am a postdoc at the CCA. And I focus mostly on mixed modes that happen during the red giant branch. And I'm trying to understand how we can use those mixed modes that we can observe fairly easily in order to investigate what is happening inside the core of the stars. So like the radiation rate, the magnetic fields, and all dynamical processes really that we can probe with that.
Hi, I'm Joel from Yale, and I'm the most junior person on the panel. I also study these mixed mode oscillators, and most of my research has concerned itself with what happens when these P and G modes are close to resonance, where you have these avoided crossing phenomena, which disrupts the more or less uniform, otherwise asymptotic spacings that we would expect, and how we can exploit these to make measurements of helium abundances and rotation and surface properties, stuff like that.
Great, thank you. So now if you could talk with your neighbors in small groups for the next 10 minutes about the topics that are listed on the top in blue through the lens of the questions that are listed below. So try to have a discussion, and I will be coming around at the end of the 10 minutes to ask you to each say something.
Shall we introduce the question first?
Oh, yeah.
All right. Sorry, everybody. Can I get your attention for a second? We maybe should introduce the questions a little bit so that you know what we had in mind. All right.
Hey, excuse me. I think. Yeah, go ahead.
So, before you start, you don't know actually what you're supposed to do. So listen here, please. All right. So we had a discussion the other day, all four of us, and came up with the most important topics, in our opinion, that need to be solved in order to be able to do more in-depth astroseismic analysis. And we came up with the following: so the magnetic fields and co. So by co, I mean spots and everything that is related to magnetic fields, right? So basically from the surface to the core, or from the core to the surface, depending on how you want to look at your star. Then we have the inertial and Raspy modes, which is a field that is relatively new in the sense that these modes have been only observed since like 5 years ago for the first time. And now we find hundreds of stars that have these modes. Then we have multi-wavelength observations and observables. This is in the context of astroseismology is incredibly important. On the main sequence, especially like 2 or 1.5 solar masses and higher up, doing mode identification, as Mai actually explained to us a bit earlier, is quite a painful experience, I can tell you. And it's only for a few stars, it's only since we observe the G-mode pulsators where we can identify the modes, and also some of the very young Delta Scuti stars that have these P-modes that we can actually do this in-depth analysis. But if we have, for the other stars, we actually require color information. So this is a very important aspect. What we also put in the same category is determining stellar parameters such as log G, temperature. I mean, we had yesterday the panel about observations. It's not a model-independent parameter. It will affect our interpretations quite dramatically. So what is it that we can do there? Time series, of course. How long can we observe? How long do we need to observe? What other satellite missions, telescope missions do we require? Then, so it's a very broad topic. Rotational splittings. So the idea is to discuss what can we actually do with already available data, specifically in the lower mass range. We have a lot of information where we can actually do angular transport analysis. And the last one, last but not least, so we put alpha mixing length parameter. I know you know that it's a very painful topic, and specifically, at least on this side of the group, I think, we would like to inspire theoreticians, especially 3D modelers, to work with 1D modelers to give us an HR diagram where we can actually go there and pick up our mixing length parameter that we require for our type of star. So that's the ultimate goal. But you can, of course, discuss mixing length parameter in whatever context you would like. Have I missed something? Okay, so please discuss and come up with 1 or 2 questions that are important that we should discuss, that you want us to ponder upon, or other colleagues in the audience.
Okay, we're going to wrap up the discussions and going to hear from the groups. Would anyone from this group like to?
So, this is loud. Yeah, we were interested in magnetic fields, and in particular, Paul was interested in a non-detection of a magnetic field, so he doesn't have to put it into his code. That's what he wants, because otherwise it's more work for the simulation people. Either thing would be really interesting, just so that we know what we should simulate when we simulate, say, a convective core. Is there a magnetic field or not? Can you tell us from seismology? Another thing we talked about was if you look at rotational splittings for fast rotators, like how reliable are these simple like 1D mode calculations, or do you need to do something more sophisticated there? So I know some people do like something two-dimensional or ray tracing or something like that. So insights there would be valuable.
Sorry, when you say rapid rotators, can you be more specific?
Something that's significantly deformed. I know I said 10% critical rotation, something like that. It's where you see significant deformation. Just an idea. Yeah, did I miss anything? Okay.
Thank you. Okay, someone from this group?
Yes, so we had a very nice discussion.
Name?
Sorry. Oh, my name is Ylva Göthberg. We were talking about. Oh, is it too far? Okay, here. It's better? Okay, nice. Yeah, nice. So we were talking about magnetic fields, very important. It would be great to have a more holistic model of magnetic fields inside of stars that cover from the core to the surface. So like that's a theoretical aspect. And maybe, if possible, to detect these modes that Lisa has been talking about, the magnetic field splitting, that degenerate with the rotations, very complicated. But if, for example, you would have a slowly spinning magnetic star, maybe massive, would be fun. Could be possible potentially to then isolate, since Mike says that main sequence stars rotate rigidly. You can see the rotation rate on the surface. Maybe then that could be a good target. But yeah, we had more things going on here, so we got a little bit interrupted. But yeah, so far so good. No, we were in the middle.
Okay, thank you. Who would like to speak over here?
We talked about a number of things.
Name?
Ben Brown. From magnetic fields and being confused about Raspy modes. But we also talked about actually the very last thing, the alpha MLT thing that was an explicit shouted out request. And we wanted to see if the community is aware that there is an AHR diagram of alpha values from 3D radiative hydrodynamic surface simulations by Rainer Trompedock and company. And so the question is, like, are those known? Are those used? And if not, what's wrong with them, right? And so, if something's wrong with them, how do we do better?
And go to the higher mass and.
Well, they don't have relevance for higher mass because you lose the surface convection zones, maybe, that set the adiabat, right? So are there surface convection zones in high mass stars that matter, that we care about, where that work's not been done? Maybe.
Thank you. Who wants to speak for this group?
I can do it briefly. Jared Goldberg. So mostly we talked about the fact that there is surface convection in massive stars, both on the main sequence, after the main sequence, and even going up the red supergiant branch. And then alpha MLT becomes pretty important and is absolutely not calibrated to 3D atmospheres. And especially deviations from spherical symmetry start to matter, and all of these other effects. In terms of useful things for asteroseismologists, though, we are a little bit at a loss, as none of us in this circle do asteroseismology, but can continue to comment, have discussions, and do have strong opinions about alpha MLT.
Okay, strong opinions noted. Anyone from this group?
Okay, we also talked about magnetic fields. This is Jim Fuller. So we came back to the age-old question of why 5 to 10% of main sequence stars are strongly magnetized. Sadly, we did not solve the problem. But we did discuss some ideas about how to think about that and observations that are relevant, fraction of stars that show magnetic fields on the pre-main sequence. This is all for massive stars. We talked about how magnetic fields might affect mass loss of massive stars, and also how they might affect the structure of the internal structure of the star, and how that might manifest as surface brightness variations across the star. But we did not discuss asteroseismology.
Thank you.
Okay, Savita Mither. So we discussed a lot of things. I think we started with the multi-wavelength observations. So also for the main sequence solar-like stars, low mass stars, it's something that could be important because different wavelengths, we can have access to different depths of the atmosphere and see differences in the convection of the stars. And this is something, for instance, we are looking into for solar G modes. After that, we talked about using the models for global seismic parameters, where we have delta nu and nu max, so the global, the mean large spacing of the acoustic modes, and trying to, because the way we are observing them come with a method where we only use either a broad range of frequencies, or sorry, or there are methods where we are only using the modes around nu max, and then the way we compare these observables with the models depend on, with the models, the delta nu is coming from a general formula, so it's not directly comparable, and we need to improve the way the models are providing the delta nu to be comparable to the observed ones. What else? Oh yeah, we talked about the atmosphere. So I mentioned briefly the surface effects, something that we didn't talk about in the 1D modeling. So it kind of goes with what Ben was saying with trying to have these patch models from the 3D simulations of convection, and also something about the atmosphere that's not correctly modeled. And I think that's all. Oh, telescopes. No, what did we say?
We said the gem band stators. We said it would be nice to have a giant piece of glass with a multi-object spectrograph on it to point at a cluster for 6 months to a year. That'd be nice.
Okay, thank you.
All right, we all knew that was going to happen anyway. Meredith Joyce. Okay, alpha MLT, obviously we talked about, but I will defer that also to tomorrow as much as possible. We also had a discussion of P modes and G modes and where they are degenerate and which parts of a star they probe, and how what is so none of us are observers. So what would actually be needed observationally to get G mode spectra that allow us to very carefully characterize stellar cores in sort of the 5 solar mass regime? So these would inform simulations that Lin Hao is interested in. So we had a conversation about that, and salty MLT things for later.
Is that like thermohaline?
Hi, Janos Stieber. We also had an interest in magnetic fields. And what context?
What's the magnetic field strength below the convection zone in RGB stars is what I said.
Okay. I'm interested in inertial wave dissipation. We talked a bit about complications in mode spectra when you have significant centrifugal distortion. Anything else? Yeah, more types of modes, I guess. Oh, latitudinal differential rotation. We're interested in whether it's possible to constrain that with asteroseismology.
Okay, and I believe there are some from Zoom.
Yeah,
So
could
Daniel, if you wanna do this.
Zoom participants, someone mention what you were discussing?
Would you like me to speak?
Yeah, we can hear you. Go ahead.
Hi, I'm Amanda Caracas. I'm speaking. I'm listening in from Melbourne, Australia, where it's right in the middle of the day. So we mostly discussed alpha MLT, probably not too surprising either. But one question that it wasn't. So I didn't pose this question. I think it was Arthur and Leon who posed this question. Was about using the full spectrum of turbulence model for convection to look into astroseismic modeling. And they wondered if anyone had done this. And I did not know the answer. I've worked with Paolo Ventura and compared AGB models, but I don't know of any work that's compared full spectrum of turbulence to astroseismic data. Maybe someone in the audience knows.
Can you clarify what you mean by that?
Yeah, so full spectrum of turbulence is an alternative model for modeling convection in stellar interiors. And I think it's only used by the Italian group, I think, but I'm not sure. And it's just a different way of treating convection. I don't know how they calibrate it. It likely has to be calibrated like with alpha MLT, but it produces a very different stellar structure, at least for evolved stars. So if you take a red giant or asymptotic giant branch star, the structure is very different compared to if you use alpha MLT. Even if you increase the mixing length theory parameter alpha to something higher, you still don't, maybe like 2 or 3, you still can't really replicate full spectrum of turbulence models. They behave very differently. So I wondered how they behave on the main sequence compared to models with MLT, and then how does that compare to astroseismic data? Well, actually, yeah, because it wasn't me who posed this question. We also wondered about alpha MLT, if it's calibrated, say, to a sun or a red giant branch, how applicable it is across the HR diagram, especially for those interested in more evolved stars, since it seems even if you calibrate it with one code to one set of data, how much that tells you of the physics, really. Anyway, maybe this is a question for the session. I probably can't attend tomorrow in your morning, but yeah, I'll leave it there.
Okay, thank you, everyone. So now let's just have a discussion. So if you have questions or comments, please raise your hand and I can bring the microphone. And panelists also have microphones. So let's talk.
Okay, so it seems we opened a can of worms, or actually 5 can of worms, which I think were opened before, to be fair. And we were very much aware that many of these topics will be and have been addressed in other panels, but that's natural because there is a collaboration between all these groups. So I would like to address a little bit the magnetic fields for the type of stars that I'm working on, so these A-type stars. There are about 10%, as Jim mentioned earlier, 10% of the stars that have very, very strong magnetic fields that are also being observed actually on the pre-main sequence in Herbig B star, A and B stars, and are therefore believed to be fossil fields. So these stars are the AP stars, and some of them actually, a fraction, which I should know, I think about 10 to 15%, are actually oscillating. So we can do seismology of those stars. They have very high radial order overtones, which means we cannot really go all the way into the depth, but we can at least probe the outer layers. There are still many things that we don't understand, and in order to excite those modes, you actually need the magnetic field to disrupt the convection in certain parts of the star in order to get the kappa mechanism to excite those modes, right? So this, I think, connects also very well with somebody saying, I think it was Ben saying, that there is no convection or that alpha mixing length parameter doesn't really matter in intermediate mass stars. I beg to differ, because from astroseismology, we actually know that depending on which mixing length parameter you're using, you can fit or not fit excitation of oscillations. they can be all over the place if you use the wrong number. There is there are many problems, but there's definitely, we definitely need that. Also, we have observations of magnetic fields that, so apart from the very strong magnetic fields, we have the lower, so either no observations at all, but the question is it because our technology is not advanced enough? So the magnetic fields do exist there, but they have very complex topologies, or we can't observe them, or are they really not at the surface to be observed? I'm personally convinced that every A-type star, every star, as a matter of fact, has a magnetic field. But, how else would you make a star without a magnetic field? The question is, can we observe it, right? And now we are starting to populate this range between the very strong magnetic fields and no detections at all, with magnetic field strengths of the order of 20 Gauss up to 60 Gauss, so very intermediate magnetic fields. What we do observe actually in hundreds of stars are spots, stellar spots, and to my knowledge, it requires some sort of magnetic field to make spots. We have thermal, well, we think we have thermal spots, but we know for sure that we observe chemical spots. Chemical spots meaning that you have an agglomeration of elements along that coincide with the topology of the magnetic field. So you can have iron spots, you can have praseodymium, neodymium, all these crazy elements that are levitated into the outer layers. Think of them as clouds if you want. And we know that these are also patches actually that oscillate with higher amplitudes than other elements. So we can actually do 3D observations of these atmospheres. Yeah, so I think that's my takeaway. Do you want to discuss magnetic fields?
For magnetic fields, I think this is partially going to touch upon what Lisa is going to say, but there have been, I'm going to stick to the main sequence, there have been efforts to use gravity mode oscillations to actually measure the near-core magnetic field strength. Earlier showed a figure by work from Jordan that actually showed the theoretically expected signature of a near-core magnetic field on a G-mode pattern. So far, for the actual detection, we have two problems. Firstly is that there seems to be very little overlap so far for stars with a measured surface magnetic field, where we know, at least where we have independent confirmation that there is a magnetic field, and where we can measure the G-modes. So I know that Daniel has been working on this. One of the possibilities is that the magnetic field, as soon as it reaches a certain strength, it actually converts the G-modes into Alfvén waves, which then dissipate. So that means that we can't observe the G-modes anymore, or we don't have any G-modes anymore as soon as you go above a certain threshold. For the star where we have a magnetic field measured at the surface and where we have G-modes, the second problem is that the effect on the frequencies, which is our main diagnostic, the effect is actually very small for the G-modes, to the point where it's almost impossible to measure accurately. So yeah, for the time being, I'm afraid on the main sequence that is difficult to do. Yeah, maybe in the future.
And for more evolved stars, it's kind of the same problem for now, is that red giant stars have a radiative interior, and the main hypothesis is that as we observe magnetic field at the surface of A stars, like big deep order fields or like low order field, like large scales, then there is no reason that we could not have the same thing inside red giants, because if it's a radiative zone that was before convective zone, and some magnetic field, some magnetic energy must have been trapped there somehow. but we don't know what is the strength of such field, and so we don't really know what to look for, because depending on the amplitude of the magnetic field, the signatures on the amplitude and on the frequency is very different. So we are building prescriptions for that, but it's like we do something and then we try to search for it, but maybe we're not looking for the right thing. Depending on the topology of the field, it can be pretty different. So it's like, I would say, a long work. We're just starting to do that because the data that we have from Kepler have just been made possible to measure the rotation rate, which is something that we know pretty well from the theory. And now we're trying to look for magnetic field that makes something even more complicated, and it was already pretty tricky for rotation. So yeah, I think we have a lot of work to do about that. But as Vicky said, I don't see any reason why the interior of a giant should not have a magnetic field pretty strong, because it's a plasma, and all plasma are magnetized basically. So I think this is something that is missing everywhere, and we are kind of ignoring it in the models. And I don't think that's, I mean, I think it can have pretty large impacts on what we're looking for, on all aspects for transport of angular momentum, and many things. And there is also the question of, I mean, it's a question for later, I suppose, but how magnetic field inside the radiative interior like communicates or relates to whatever is happening on the convective envelope, because there must be some connections there, and I think it's something that could be interesting to look at. Like, is there any way we could see, we could have an idea of what is happening inside by looking at what is happening at the surface for solar-like stars, for instance, where it's probably more easy to do spectroscopy. So yeah, that's my thought.
Okay, we've been talking about solar-like stars, but I'm going to do something that's probably not very wise and talk about the sun. So the reason for this is because the observational and methodological techniques we use to measure magnetic fields and differential rotation and so forth, in large part for solar-like oscillations, are mostly inherited from helioseismology, right? So the observational signature of both magnetic fields and latitudinal differential rotation is that when you have a rotationally split multiplet, both of these induce asymmetric components into the rotational splitting. In helioseismology, this degeneracy, in the sense that both of these phenomena give you the kind of asymmetries, this degeneracy is resolved by the introduction of high degree, that is high L modes, which you can obtain from resolved disk Dopplergrams or imaging and so forth. And that's not observationally available to us for these evolved stars. Additionally, for these evolved stars, because you have G modes interacting with P modes and using avoided crossings, you also get additional asymmetries in the rotational multiplets arising from the avoided crossings as the P and G modes evolve independently. So that is, I think, a major methodological obstacle to measurements of either latitudinal differential rotation or magnetic fields, or potentially both in the same stars. Another open problem that hasn't really, I think, been dealt with in helioseismology, and therefore as solar-like astroseismologists, we kind of inherit this problem, is that the excitation of solar-like P modes is directly from coupling to the turbulent velocity field in the superadiabatic layer, right? And since you can't handle convection well in 1D models, we basically just don't use the amplitudes of modes we get at all in stellar modeling, at least for these solar-like P modes. And rather than trying to resolve these problems, the helioseismologists decided just to move over to astroseismology and hunt the problem down to a future generation, which is us. And I understand that most of this work was done when I was a baby, but it's still fairly unsatisfactory to be in this position now and realize that no one has been trying to solve these problems, or at best have been running a bunch of 3D simulations of the solar atmosphere, seeing some modes being excited and calling it a day, without further attempts to crystallize some analytic or at least asymptotic insight out of this. Yeah, sorry for sounding salty. It's just like this is what my advisor and I talk about all the time. So.
Hi, Meredith Joyce. I just want to put in a quick pitch for former PhD student Yixiao Zhou, who is simulating amplitudes of solar-like oscillations in 3D, and I think that's the state of the art.
I think I can just talk. Yeah. Daniel Quene. So it's getting kind of late in the afternoon. I just want to throw some spice in. So here's my claim. If you're looking at G modes and you have a magnetic field, I think that either the magnetic field is weak enough that you can't tell the effect of the field on the G modes, or it's strong enough that you don't have G modes anymore. So I think that, yeah, so that's my claim. And then more spice. So I've worked with like Jim and Matteo on looking at these depressed dipole modes in RGB stars, and I kind of like our explanation that that's due to core magnetic fields which are suppressing these modes. But there's a problem, which is that my understanding is that the modes are only depressed in about half the stars, which says that half the stars have a strong enough magnetic field for this to work, half don't have a strong enough magnetic field for this to work. Where does that come from? Why would it be 50%? That seems really strange. It's been a huge question for me. So I think it's a very unsatisfactory part of that theory. What mass regime, Jim?
It is about like 1.1 solar masses. So it corresponds to the intermediate mass stars on the main sequence that develop the convective core. So the main idea is that the convective core during the main sequence generates a dynamo field, and then this field remains trapped inside the red giant radiative interior when the star evolves. But can go ahead.
Yeah, so it's about 20% of red giants in the Kepler field, and it's about 50% of stars over 1.4 solar masses. So it's actually, not only they have to have a convective core, they have to be more than about 1.4 solar masses instead of 1.2, which we also don't understand. So why the number is 50% for those and not 100%, we don't understand. Why 8% of massive stars are magnetic, we don't understand. Why 20% of white dwarfs are magnetic, we don't understand. So it's always some fraction of about 5 to 50%, and where that number comes from is not clear.
And it's also that the amplitude is not like we have normal modes or no modes. We also have stars for which the amplitude is just in between. They are not a lot, but we still observe that, which is also very weird.
This is Dominic. On spicy comment number 1, I think that's fine. I don't see why that would be controversial, but between those two things, there's going to be a transition, and I think that's where we can do things. So that I think that's an interesting regime, and that's one of the things we were talking about when we did our breakout session. Is that I think so? Mai showed this plot from a paper from Jordan from last year. There is a regime between about 10 to the 5 and 10 to the 6 Gauss in the core under all assumptions that we should be able to constrain the magnetic field strength in the core of these SBB stars, well, G-mode pulsators. On comment number 2, I think it's important to bear in mind that the Kepler field is very biased towards low mass red giants. So this 50%, I think, has a big caveat on it. It may be plus or minus 20% in either direction, because we haven't done seismology in the Kepler field of high mass red giants. So maybe the fraction increases as a function of mass, maybe it flattens off. It's something that I think is important to keep in mind when we talk about 50%.
Jim says that it was measured to be about 50% from 1.4 to 2 solar masses. So in that mass range, it was a bit flat.
In that mass range, yes, but the above that as well, I think is interesting to probe, because those 3, 4, 5 solar mass stars are the descendants of these potentially strongly magnetized SBB stars. Because we always talk about the descendants of the SPB stars being red giants, but actually it's a very different mass range. And so maybe in the intermediate mass stars, that's something that is distinctly different from 50%. We don't know, but I think that's something we can possibly do.
So this is a question I've been asking observers for several years now. This is Jim Fuller again. And maybe you can give me an update. We would like to know what fraction of stars in the Gamma Doradus or SPB instability strip actually pulsate in G modes. So because if there's a strong magnetic field near the core of those stars, that would suggest they should not be able to pulsate. So if you just look at the fraction that don't pulsate, you might be able to infer that those stars have strong magnetic fields in their cores. So I was wondering if the observers can tell us whether or not that measurement is possible.
I'm going to start off by saying that, yes, I would very much like to know the answer to that question too. The main problem that we've actually had so far is that most of the known gamma dors and SPB stars were in the Kepler field, where the stars were too faint for us to get good spectroscopy to actually put them sufficiently accurately on the HR diagram. So especially the gamma dor instability strip, that's like 600-ish Kelvin wide. I mean, if you don't have high resolution spectroscopy, the width of the instability strip is your error. You're not going to get any pulsator fraction from that. So it's only now with TESS and with large sample surveys, spectroscopic sample surveys like SDSS5 in the near future, that we will hopefully be able to solve that question. But yeah, I very much look forward to know the answer to that too.
Does Gaia not help? Gaia should give you better temperatures without spectroscopy.
Not really yet, because it helps in the sense that, yes, we get a parallax, but the temperatures that we get from Gaia are not sufficiently accurate. And if we get a temperature from a Gaia measured star, that's also dependent on the reddening and the extinction. And those maps simply aren't really accurate enough for our purposes.
If I may add to that, the problem is that for some few stars where we actually believe that the stellar parameters are okay, we see that actually G-mode pulsations or let me rephrase, we see peaks in the range where we expect G-modes. I want to be very specific here, at temperatures where the excitation mechanism should not operate. So in other words, at 8,000 Kelvin, we find something that looks like a gamma door. There are few stars that definitely are there. So that's something that will not help answering your question.
Yeah, I think it's really difficult. This is Dominic again. So the paper that I also talked about, so Gang Li's sample, it has a series of papers on Gamma Doradus stars observed by Kepler, 600-ish stars, let's say. And that's actually the opposite way around of tackling the problem, where we said, oh, I don't care about my spectroscopy. Say, let's just look for Gamma Dor stars in the Kepler field, and you find this many. And then you look as a fraction of the total sample. And I think in that sort of rough temperature regime, we're looking on the order of maybe 10, 15,000 stars. So I think we're looking at something on the order of 10%, but that is plus or minus a lot. The pulsator fraction to the stars in the sample.
G-mode pulsator.
In the G-mode Gamma Dor sample, yeah. So if you take the Kepler sample of A and F stars on the main sequence, the fraction that has G-modes is about 10%.
If I may pick up on that.
Can you hold it closer to your mouth, Timothy? It's very quiet for me.
Okay, sorry. One caveat with that is that the way that Li Gang selected his sample was by saying, okay, you have these stars where you have a low frequency power excess, and then he looked for period spacing patterns, and the star was accepted as a gamma dor if it had a G-mode period spacing pattern that he could fit. So if you have a G-mode pulsator with a very strong resonance at 1, 2, or 3 frequencies, it will not have been in a sample. So what Dominic says is true, but that will very much be under a bottom limit of the actual pulsator fraction. Yeah.
Question from Amanda via Zoom. For magnetic white dwarfs, could a binary merger explain some of the observations?
Do we have experts?
Ilva says yes. I knew she would say yes.
Yes, so there was a really nice work by Ilaria Caiazzo at Caltech during the past 2 years on magnetic white dwarfs, where she showed that she found a really magnetized white dwarf of like 800 megagauss, and it's also spinning every 7 minutes. So that is probably a really good candidate for a merger scenario during the white dwarf stage, so two white dwarfs merging with each other. The other white dwarfs that are magnetized, a little bit less clear whether they are merger products in the sense that maybe there were two stars during the main sequence phase or so that merge with each other. I don't know. Or interiors of stars are just magnetized. It's also interesting. They're magnetized stuff.
So maybe to add to that and bring out some more work, this is Matteo Cantiello, bring out some more work from Ilaria Caiazzo you just mentioned. She also published a paper where she showed using clusters that actually some magnetized white dwarf actually had evolved as single stars. So magnetized white dwarf might come from actually two different channels.
So to comment on that work, which I also like very much, this is Ylva again. It could be that, yes, even though that's very young white dwarfs, that they were merger products during the living star stage. But then I agree, it's possible. I also acknowledge the fact that they could have been single. Like 5 solar mass thing is with magnetized cores.
I would like to go a little, Vicky here. I would like to go back a little bit to the red giants and the magnetic fields there. So my general understanding is that these magnetic fields must have formed in 2 ways. So either they're fossil fields, right? So, and or generated around the core of the convective core, or have something to do with the surface convection. So I wonder, we actually discussed that over lunch. A significant number of intermediate mass stars rotate actually very fast. So if you have an oblate star, right, you will have a convective, you may end up with a convective torus around the equator. And temperatures that are slightly higher at the poles. Would you not be able to drive a dynamo in this way? It's a question for the theorists here. That could explain the observations on the red giant. And
Ben? Dynamo?
I know his answer, but maybe you want to share it as well.
My answer at lunch was, seems like it could, maybe, sure, why not? It's rotating, they have alignments, they're just doing it in a little wedge. And then I said, it's a Boozy annulus. And, you know, that kind of derailed lunch.
All right, any more comments on magnetic fields?
So this is Jamie. So this is relevant to magnetic fields, but also more generally, like people work on this in different parts of the HR diagram on different types of stars. How do we put all of those pieces together into some physical understanding? Do you guys have suggestions or thoughts about how that could happen?
I guess programs like this here, where you actually get people from different communities working on different types of stars. Because I also realized when the question was there with white dwarfs, I know very little about white dwarfs, right? So we need to sit down and exchange our experience on observations, on theory, and so on. I think that's the way to go.
Sure, I can talk. Okay. My take on this is that I can only speak for, again, solar-like oscillators, right? But we have some measurements of, solar-like oscillations on main sequence stars from Kepler, and then we have a ridiculously large number of like red giants in the Kepler field as well. But in between, in the subgiants, we don't really have very much except for like maybe some 1 year long time series from TESS. And so even if we were to make definitive measurements of magnetic field strengths and topologies for main sequence stars and red giants with these statistically large samples, we're not at this time, I think, able to observationally constrain the evolution from one part of the HR diagram to the other. And so this, I think, goes back to measurements we would want to make. I think in this case, then it would be very helpful to have a statistically large sample of oscillating subgiants, both because it's an intermediate phase of evolution, and also because like you get a very large variation in the internal morphology of these stars as they cross the Hertzsprung gap.
All right, shall we move on to the next topic? I yield the floor to you.
Okay. Well, Raspy modes was a slightly less popular topic than magnetic fields. Yeah, the one, yeah.
I think it was pretty popular though. I've heard it at least twice.
Okay. Well, in physical relevance, right. I think the main point where that can actually contribute is related to the question that came up in terms of the possibility to constrain differential rotation and complications from centrifugal acceleration for the rotation measurement and for the rotation profile measurement. So this is actually a good point to expand a bit on that. So to recap, if you have an R mode, essentially what you have is a large-scale toroidal motion on the stellar surface, or in general. So it's basically like if you have a tornado on Earth. But the thing is, such a toroidal motion will not generate a temperature variation, so we can't observe that. So in a rotating star, the Coriolis force will couple that to an actual observable oscillation with a temperature variation. Now, things get interesting if you add differential rotation to that, not just rigid rotation, because what will happen in the case of differential rotation is that observable oscillation will become more sensitive to the more slowly rotating part of the star. So if you have a faster rotating core and a slower rotating envelope, the stronger that the differential rotation is, the more sensitive that Raspy mode or those Raspy modes will be to the outer layers of the star. Whereas for a prograde mode, like a typical prograde dipole or a Kelvin mode, those will become more sensitive to the near core region. So if you have those patterns, by comparing them and accurately modeling them, you can't place constraints on the differential rotation profile. So that's where they can actually contribute most. I should add, in terms of complication of centrifugal acceleration, we've looked at that so far in the case of uniform rotation, and so in that case, the modes, or at least also the R modes, will be most sensitive or stay most sensitive to the near core region, where the effects of the centrifugal acceleration are smallest, and then the effect is small enough that we won't observe it. But what actually happens if you combine centrifugal acceleration with differential rotation, that I don't know. So it may be that in that case, the situation may be a little bit more complex. But yeah, that is actually where, for the time being, the strongest contribution from R modes lies.
Daniel Quine, I have a question about these R modes. So first a confession, I don't actually know what Raspy modes are, but I know that they're real because they're observed in the atmosphere. And in the atmosphere, not only do they see Raspy modes, they also talk about Kelvin waves and also Unai modes, I think. Why do people not talk about those in the context of stars? And can you maybe say what the difference are between these different types of waves?
Actually, it may be easier if I start to draw things. Yeah, true. Okay, I will do my best without a diagram. But so we actually do have Kelvin modes. So if we have prograde dipole modes or prograde dipole G modes, those are the Kelvin modes. The reason that we don't tend to use that term is because it's just not common within astroseismology. And if we have a slowly rotating star, then we just talk about prograde dipole modes because then the Coriolis force doesn't really matter. But yeah, we do have them. In the case of Unai modes, they actually have been observed in Olaf Gang's sample. Out of all 600 stars, there was one with a detection. The reason for that is that those Unai modes, so a normal R mode that we observe will have two vortices. They will have two toroidal motions, one above the equator, one below, but both of those will have the same temperature variation. That will be in phase. It's an even mode. But in the case of a Unai mode, there will be one global vortex, one global toroidal motion from pole to pole. So it will have to compete with the horizontal motion of the Kelvin modes of the rotation itself, for one thing. But also the temperature variation associated with that is it has an opposite sign above and below the equator. It will be positive above or and negative below, or vice versa. And if you then integrate over the stellar surface, the effects will cancel out and they will be very hard to observe. But yeah, they very likely are present. Oh, sorry. Yeah, I hope everyone could still hear me, but yeah, Unai modes are present, most likely, but just very hard to observe.
Thanks.
I would like actually to make also the connection from Raspy modes to magnetic fields. We have a sample, so it turns out that the Kepler data are still giving us a lot of things to think about. So we have a sample of about 200 plus stars where we see these Raspy modes, or at least this is our interpretation, where we see Raspy modes that are excited by a spot, which, I mean, again, in order to have spots, you need some sort of magnetic field. The entire, I mean, there is a lot we have to figure out, including stellar parameters and so on, but I think that's very interesting. And the idea, the interpretation by Hideyuki Sayo is that these Raspy modes are excited by the spot. Now, please don't ask me how, because I'm still trying to wrap my head around that. But it seems that we can also connect this to magnetic fields, which I think is very interesting. More questions on that?
Hi, this is Meredith again. I don't know if this is a question, but it's like maybe a framework where people can like correct me or like start a conversation or whatever. But like my general understanding of how like any kind of star with a surface convective envelope works, whether or not that star also has a core convection zone, which is a key thing to remember when we're talking about calibrating MLT in particular, is you can have core convective stars where you can still calibrate MLT. So magnetism creates spots, say, right? Spots impede convection, convection drives waves, ergo cluster F, right? So is this the correct line of thinking about how all of these things interact?
I'm not taking that one.
Cluster F is the answer, yeah. I don't think I can add much to that, to be honest, because disentangling all these different aspects is one of the main issues. And from my perspective, I think trying to really understand the excitation of many pulsators can teach us something about these parameters. Because we know that magnetic fields will impede or will damp modes, at least that's what the observation suggests, whereas we also need some sort of convection in order to have this excitation. So if we manage to somehow calibrate these with models, I think that's a way to go.
Daniel Quene, my understanding is that in the atmosphere, things like the jet stream are actually sharpened by Raspy waves. That's an example where you have a small feature which can still excite these waves. So maybe this is a similar mechanism to, or somehow related to spots involved with wave excitation.
Yeah, it could be. That's true. Shall we move on then to, you choose which we should go next.
Okay, so maybe we can talk about the second last thing, like if we had control of the field, what we would like to see happen and why. I guess I should recuse myself from this discussion because it's not a good idea to give a grad student infinite money, but it would be like really nice to hear what the like more experienced people have to say about this.
So we're talking about the rotational splitting, right?
If you had control of the field.
Ah, right. Oh.
You're the one who wrote that down.
Well, yeah, it was part of the questions that we got from the organizers. Yes. So, does anyone want to start, or shall I start?
I think Jen has.
Oh, please go ahead. No, you start. I'm talking all the time. You start.
Okay, Jim Van Saders. It's this idea of having, if you had a really nice big telescope, right, with a multi-object spectrograph, so you can do asteroseismology from the ground, and you have complete control over it, so you don't have to look at anything else, so you can get nice data. You're not going to have multi-site, but whatever. And you pointed out an open cluster where you can control for the age and the metallicity. You get stars of a bunch of different masses. You can look at mixing length calibration. You can look at convective overshooting in the massive things. You can pick a cluster that has blue stragglers in it, so you get to look at merger products. Like there's so much you could do with the dimensions of age and metallicity removed from the problem if you had infinite money.
There is also a similar question to what I think was this morning we were talking about, how we can acknowledge the work of people working on hardcore, like the 3D modelings. We have the same thing with seismology, which is the data that when they come from space mission, we cannot use them right away. We have to calibrate everything. It takes a lot of time. And for instance, for the TESS mission, there have been like a collaborative effort trying to do that with the task and the TADA collaboration. I guess I wanted to say that there are, for instance, students who are working on calibrating the data, classifying the stars, and are we giving them credit for that enough? So this is, I think, a big question because we need that. Otherwise, we cannot work. On Kepler, Rafael Garcia has been mostly calibrating everything, which is great. But maybe we need more people to focus on that for the next missions. So.
Yeah. So Rafa Garcia. If we have infinite money, I would say that we have to bring back one idea that Jorn had 10 years ago, something like that, which is the stellar imager. So it's just putting another piece of glass, but in space. But in this case, you can have up to something like resolve stars, the brightest ones, and have modes up to L equals 6, 9, something like that, which gives you then access to latitudinal rotation, differential rotation, etc. So this is an idea that came up and expensive, of course. The second one is much less expensive. So you have just 10 Kepler missions up there with 100 of reaction wheels each. And then we will have nearly much better than what Kepler TESS is doing. And one final thing, which is what Lisa was saying. So there's a huge effort in TESS, and it was in Kepler, to calibrate the data, etc., because we were doing things that the mission was not supposed to be doing. I mean, Kepler was an exoplanet mission, and we wanted to do Asteroseismology. It was a community service. In Plato, for example, everything is in the pipeline. Everything which is part of the mission. So the data will be calibrated, etc., to do what are the objectives of the mission. So we have to separate a little bit the things in the sense that I'm sure that the TESS people were doing a pipeline to do exoplanet research, because this is what the mission was intended to do. And what we are doing with the data is another different thing. But of course, we need the money and the credits and everything for the people that are doing the job.
Okay, so I have a radical suggestion. What if we had no money?
What if we get no money?
Like, what would we prioritize if we basically ran out of money and had to like figure out what to save immediately?
So in that case, Rafa again, we have a lot of archival data already that is not exploited at 100%. As an example, the red giants, we're doing seismic parameters, global seismic parameters, and we have to do what it's intended to be, which is the individual modes, and use all of these individual modes. Nobody is using grid modeling within individual modes, for example. So.
Vicky here. I also believe that we should we have to go, so with all the new knowledge that we have based on how our models have been improved and also understanding of our observations, I think we have to go back and reanalyze many of the data sets. For example, the Kepler data, I mean, also solar oscillators, all type of stars. With the knowledge we have today, I think we would find new aspects that we can attack scientifically. Also with the TESS data, the TESS data. We can access completely new types of stars that were not observable before. As a comment to the bigger missions, the problem with the bigger missions and the funding is that it takes usually 20 years from proposing a mission, a big mission that is, until it's flying, and usually it ends up 3 times more expensive than it's intended, at least based on available data. And I think we should really explore the idea of going smaller in mission. We don't have to fly all the time Keplers or JWSTs or Hubbles. I think so. What Dom presented, I think, was it? It was on Friday. Okay, sorry, my timeline is a bit out of shape. So he presented the idea of having a nanosatellite that is observing B-types and O-type stars spectroscopically. High-resolution spectra of a very narrow wavelength region to get mode identification and other scientific aspects. I'm personally also working on a low-resolution broadband spectrograph that should cover wavelengths from 250 nanometers to 700 to be mounted on a nanosatellite. And the design is actually pretty far. I just need the money to fly the satellite. So, but still, it's the costs that are associated with a small mission are significantly lower than Kepler JWST. And I think we can still get a lot of information.
So another question. It feels like Jamie. Hi. It feels like the astroseismologists have convinced people that they can do awesome things, and now when you give us results, they're to 10 decimal places, and people are like, so where's the latitudinal differential rotation? So like, how do you want to build expectations of what seismology can do, and what the real uncertainties are, and what things will never be possible versus, like, obviously you want to talk about the things that are awesome, but also what doesn't it do?
Okay, I guess I can go, although I don't think I'm qualified. So a lot of the latitudinal dependence in helioseismology comes, like I said earlier, from high-degree modes, which we don't have for stars that are not the sun, unless you want to buy your very own interferometer to like stare at one star non-stop for 6 years or something. So I guess in terms of managing expectations, I suppose that astroseismology is a victim of the overwhelming successes of helioseismology. And I don't really, this seems to be like a cultural and rather than a technical issue, so I don't really know what a good solution is.
So what we are limited by are, I would say, two major things. The first one is the frequency resolution that we have in our data, which corresponds to the duration of the observation. So the longer we observe, the better the result will be, and we will be able to investigate more detailed things, such as the magnetic field. This is why we're looking a lot at Kepler data, because the 4-year field is very, very precious for us. But doesn't mean that Plato cannot do better than that. So there is still a lot of things that we can do. And the second problem that we have is the signal to noise ratio, depending on the detector. And this is also something that can be improved in future missions. So I would say that we are not like, this is not something that we're limited intrinsically. It's more about how we can improve those things to do more. And I don't see a lot of things that we really cannot do if we put the efforts on it.
So I'd like to now ask each panelist to give, say, 2 minutes of your takeaways from this panel.
Takeaways, okay.
Okay, yeah.
Main takeaway for me, let's see. Clearly, I need to care more about magnetic fields. That is obvious. And yeah, that's actually the main one. But yeah, if I have to choose something specific that might actually be manageable, is the suggestion. I don't remember who came. I don't remember who came up with it originally. I'm sorry. But to also look more at latitudinal differential rotation, because so far I've actually been most focused on the radial dependence, slightly biased by the 1D evolution codes. But yeah, that's clearly something that from my end, at least, I think that's reasonable to do.
So I guess I'm going to speak about magnetic fields, of course. I really like the fact that people seem interested in looking at magnetic field along the evolution of stars. I think this is something that we don't talk about much and could be improved a lot, from the pre-main sequence to the main sequence, like massive stars, intermediate mass stars, low mass stars. It's not an evolution, but like it is on the Hertzsprung-Russell diagram at least. And yeah, I think we could benefit from that because we are all looking at our own stars a little bit blindly. And this is true. This is something, for instance, Vicky mentioned last week, is that the percentage of red giants that seems to show magnetic field due to the amplitude of the modes is not the same ratio as the star on the main sequence that show magnetic field. And why is it like that? So yeah, I think I'm going to conclude on the synergy that are possible, depending on the mass of the star and the evolutionary stage.
Okay, me again. I just want to observe that we've been talking with a lot of like fond nostalgia for how amazing Kepler was as a data set, which tells me that, you know, right now the primary limitations we are running into with these new data sets are probably that they're not long enough compared to Kepler, because Kepler was a 4-year-long data set. At the same time, I'm applying to postdocs now, and it does not escape my notice that the length of the Kepler data set, and the reason why it's so good, is that the length of the Kepler time series are usually longer than the duration of one postdoc. So yeah, even if we were to launch a comparably good, and by good I mean long baseline space mission now, I wouldn't be able to get around to processing that data and saying anything interesting, at least within my first postdoc, if I stay in the field that long. So yeah, I then wonder, how likely is it for us to be able to get another data set of comparable length? Because that seems to be the main limitation for our ability to do continued astroseismology of like comparable quality to the Kepler days in the immediate future. Now that TESS has shown us that you need long time series.
All right, so Vicky here. My takeaway here is, first of all, we didn't even get through half of the topics. So I guess it means that there are a lot of things to discuss. And I think the most important part is to realize that astroseismologists alone cannot solve anything. We need to work together, different communities coming together. And I also realized during the last 2 days that we also need to learn each other's vocabulary. That is something that limits my understanding of several talks, because I cannot understand what it is because I use different terms. So I think there is a lot more work to do there. And in terms of observations, I think, at least for an intermediate master regime, we definitely need multicolor photometry or spectroscopy, multicolor observations, simply because we need to identify the modes to the same precision as in solar-like stars to be able to actually measure the differential rotation inside the star or the latitudinal one. And I think in terms of length of observations, to answer your question, is Kepler, do we get anything after Kepler? TESS is now observing for several more years, right? So in principle, we can actually even get more data than with Kepler. There will be gaps of a year, roughly, but we can get these observations. And I think there is a lot that we can do also, especially for the bright stars, where we can do ground-based follow-up. All these stellar parameters that we didn't have time to address, or we talked about yesterday during the observational panel. So I think we still have a bright future. It sounds like everything is negative and we don't understand magnetic fields and we don't understand convection, nothing. I still think there has been a lot of progress in the last 5 years. So let's focus a little bit also on the positive things. Yeah, that's my takeaway.
Great. So on that note, let's thank the panel.